Steel design, compression members, effective length factor. In the previous lecture, the application of the Euler-Buckling equation for determining the compressive strength of simply supported columns was discussed. The Euler equation gives us the compressive stress that, if reached, causes the member to buckle. This equation is defined in terms of the moment of inertia of the column's cross-section, the material's modulus of elasticity, and the member's overall length. This formulation assumes the column is pin-connected at its ends. Under these boundary conditions, the buckled shape of the member looks like this. But what if the member is subjected to different boundary conditions? In this lecture, we examine the impact of various boundary conditions on the compressive strength of columns. Suppose we replace this pin support with a fixed support. How does this change affect the buckled shape of the column? Since buckling is a lateral member deflection, we can conclude that the buckled column takes this shape. Note the rotation of the column at its fixed end. It is 0. This curve has an inflection point. At the inflection point, the curvature of the column changes direction. If we refer to this portion of the curve as concave down, past this point, the curve becomes concave up. This distance is 0.7 L, where L is the overall length of the column. If we examine these two shapes closely, we can see that this curve segment resembles this column's buckled shape. Both curves have a single curvature with rotated ends. Therefore, we can apply the Euler-Buckling equation to this column by replacing L with 0.7 L. 0.7 is the column's effective length factor. Hence, the general form of the Euler-Buckling equation can be written as Consider the case where both ends of the column are fixed, forcing the member to buckle like this. This curve has two inflection points. The middle segment of the curve resembles the entire buckled shape of the simply supported column. The length associated with the curve segment is 0.5 L. Hence, the effective length factor K for a column fixed at both ends is 0.5. So, the buckling equation for the column becomes Consider the case where one end of the column is fixed and the other is free. In this case, the column buckles like this. This curve matches half of this curve. To arrive at a full curve that resembles the buckled shape of the simply supported column, we can draw a mirror image of this curve. Since these two curves have the same curvature and end rotations, we can write the Euler-Buckling equation for the cantilever column using an effective length factor of 2. Why a K of 2? Because this entire length is twice as long as the length of the simply supported column. Here are the theoretical K values for several columns with idealized boundary conditions. For design purposes, the AISC manual recommends using more conservative K values. However, some columns in frame structures may not have idealized boundary conditions. For such columns, these K values may not be applicable. Therefore, we need to adopt alternative formulations when determining the effective length factor for columns with non-idealized ends. A frame structure subjected to loads deforms. Consider a typical column in such a structure. Let's refer to the effective length of the column as KL, where K is effective length factor and L is the overall length of the member. Note that the ends of the column do not adhere to the idealized boundary conditions discussed previously. So how are we to calculate K for such a column? The structural elements attached to the column ends provide resistance against the end rotations. Using the stiffness of these elements, we can estimate the K value for the column. Let's label the ends of the column as A and B, and use GA and GB to denote the stiffness factors at the column ends. We can estimate K for the column using these factors, also called stiffness ratios. Before we get into how K can be estimated using GA and GB, let's see how these ratios are determined. Note that joint A connects two columns and two beams. We refer to the ratio EI over L for each member as its stiffness coefficient. The total stiffness at the joint due to the columns can be written as, and the total joint stiffness due to the connected beams can be expressed as. The stiffness ratio GA is the ratio of SC to SB. Suppose the frame members share a constant modulus of elasticity, E. Here we are assuming the members behave elastically, resulting in a constant E. Furthermore, let the moment of inertia of the columns be I, and use 2I for the moment of inertia of the beams. Assuming the beam and column lengths are, we can write S sub C as, and S sub B can be written as. Hence, GA becomes. We can determine GB in a similar manner. The total column stiffness for the lower end of the member can be written as, and the total beam stiffness restraining the column end is, so GB equals. Knowing GA and GB, we are in a position to determine the column's effective length factor. K can be determined using the alignment charts provided in the AISC manual. The manual gives two alignment charts, one chart for unbraced frames, frames that can undergo side sway, and one chart for braced frames, frames for which side sway is negligible. These charts represent the underlying stability analysis equations for determining K. Since frame stability analysis is an involved process, the AISC manual recommends using the alignment charts instead when appropriate. We are going to show the use of these charts in this lecture. In addition, let's consider an alternative method, a pair of equations, for calculating K. These equations were first reported in the French design rules for steel structures. Generally, the values obtained from these equations closely approximate the values given by the alignment charts. When used properly, both techniques provide acceptable values for K. Using the alignment charts, we wish to determine the effective length factor for column AB. Since side sway is not prohibited in this frame, we need to use the alignment chart for unbraced frames. First, we locate GA and GB on these two vertical axes. For GA, we have 0.44, which is located here, and 0.55 on the GB axis is located here. Next, we connect these 2 points using a straight line. The line intersects the K-axis. The point of intersection gives us the value for K. So, according to the alignment chart, the effective length factor for column AB is 1.16. For comparison purposes, let's determine K using the French design rules for steel structures equations. The equation for unbraced frames is, substituting 0.44 for GA and 0.55 for GB, we get. So, the equation yields an effective length factor of 1.18 for the column. Note that this value is very close to the value we obtained using the alignment chart. We will solve more example problems on effective length factor in the next lecture. See if you can solve the following exercise problems.